everybody, and welcome to the Oldfield Consultancy podcast. I'm your host, Marie Oldfield, and we've got Richard Saldanha with us today. How are you doing, Richard?
I'm very well, thank you, Marie. Delighted to be with you.
So Dr. Richard Saldanha is, and I want to get this right, a visiting lecturer in statistical machine learning at Queen Mary, London. He's an expert in statistical machine learning and quantitative finance. He co-heads Oxquant, a management consultancy business involved in artificial intelligence and machine learning advisory work in finance and other knowledge-based industries. Richard's worked in quantitative finance for over 23 years, and he's held senior roles in both asset management and investment banking at major institutions in the City of London in the areas of risk management, trading and investments. So now that I've managed to actually say that, Richard, it would be great to know kind of a bit more about your background and how you got where you are.
Thank you, Marie. That was a very nice introduction. Essentially, I'm an applied mathematician. My doctorate is in statistics. That was graph theory and multivariate analysis, but very much the applied end of the spectrum. And what I've done is I've basically applied my trade as a pretty half decent applied mathematician for many years, and it's kept me gainfully employed as a risk manager in the City of London, as well as a fund manager at other times where I've been involved in directly managing investments. But the common thread is that I've always taken a quantitative view of the investment world. And now I've moved into sort of portfolio mode. And as you mentioned, I run Oxquant Consulting. We get involved in a range of projects for knowledge-based industries generally. Big bias in terms of finance, because the people involved in Oxquant, that's the industry that they've worked in the most. But we've been involved in healthcare and also energy. But what we're doing is we're using some very generic techniques, basically across all these industries. And I think that intelligent, people often don't realize just how useful and how generic applied mathematics, statistics generally can be, and in what areas these techniques can be applied. And they can be applied extremely generally and are extremely powerful.
So on that, I'm going to throw the very first question out there. In your opinion, what is AI? Does it exist? What is it?
Well, the sort of flippant answer is that if I'm looking for funding, it's AI. If I'm looking to recruit someone, it's machine learning. And when we really get down to it, it's simply a regression model. And that's very much the sort of tongue-in-cheek flippant answer. The more sort of sensible answer is that you're absolutely correct. I don't believe that hard AI exists at this precise moment in time. There is an awful lot of propaganda out there in terms of AI. Most people don't understand what it is. If I talk about hard AI, what I'm talking about is an algorithm. It could be a robot, but basically it's something encoded in silicon that will react in a sensible manner, in much the same way that an intelligent human being would act, but in pretty much any situation. And I mean, you can immediately see that we are decades away from anything that sort of can behave in that manner. There are hints at what might be possible if we look at sort of DeepMind and the work that they've done on protein folding, but also game playing. That is a hint at what might be possible, because what they're doing there is they're using single methods, single algorithms, convolutional neural networks to be more precise, to basically tackle different situational problems. If we take sort of AlphaZero for chess, conventional chess, shogi, Japanese chess, and Go, it's essentially the same algorithm that's playing those three different games. But obviously they are closed systems. Those are much easier problems than sort of real world problems that we're talking about, if we were to say that sort of true AI, hard AI actually existed at this time. So what is AI? Well, there's no precise definition for what that is. I know lots of people attempt to sort of describe what AI is and how that's distinct from machine learning. Personally, I think we live in a largely machine learning world at this precise moment in time. A lot of things that are referred to as AI are actually machine learning, and there are some incredibly novel techniques that are being used in machine learning. So I like to think in terms of sort of hard machine learning, if you like, genuine machine learning. So that's basically the derivation and use of models, whereby I use the output from those models to make decisions, and that can be a completely automated process. And I think that's hugely powerful, and that's sort of the space that we are, where in my view, that's exactly where we are at this precise moment in time.
And when we talk about this as scientists, we say things like neural networks and machine learning, and it's very difficult for the normal person to kind of understand what that actually means behind it, and it's got an air of mystery around it. If you were going to kind of explain what is actual machine learning to somebody that had never came across it before, how would you describe it?
Well, it's basically the description of data. Any sort of machine learning system is built on data. Having the correct data to hand, using the right data in order to build that model, building essentially a mathematical model of those data, a data description, and using it typically in a predictive manner. Machine learning problems typically fall into two classes. They are, or rather, if I want to sort of set up a machine learning problem, it's useful to be able to set that problem up in one of two ways. Either as a regression problem, most people are familiar with regression. Basically, what I'm going to do is I'm going to estimate some parameters based on the data in hand and use that model to basically describe some sort of target. So I have some variable that I'm particularly interested in, and it could be something as simple as, say, heights of individuals in the population. And so what I do is I go and sample, take a random sample of people within the population. I'm going to measure some other attributes as well. And what I do is I try and predict those heights based on those attributes that I've measured. So sex, for example, men and women, on average, I would expect men to have a higher average height than women. And so that's it's a perfectly legitimate analysis. It's merely a simple regression. And I might then use that model in a predictive manner. So basically, I try and predict the height of people for which I don't know their heights, but I have measured their other attributes. And that, in essence, is what machine learning is about. We can make it more. The problems can become more complicated, but in a regression context, that's a regression problem. Classification problem, on the other hand, is similar but different. What I'm going to do is I'm going to measure attributes, but instead of having well, we describe it as a continuous response. Height is a continuous response. We have groups or classes. And what I'm going to try and do is I'm going to try and differentiate or distinguish between these classes based on those attributes. And you might say, well, that sounds very simple. Why is that powerful? Well, the ability to sort of classify groups of objects, could be individuals, for any number of reasons, can be hugely informative. So, for example, if I'm issuing credit cards, I would have certain measures that I might obtain. So these variables such as income, amount of borrowing, existing borrowing, socioeconomic grouping, variables of that type, car ownership, home ownership, that sort of thing. Put that all together, and then I might classify individuals in terms of the amount of credit that I might extend to them. And there might be five groups of or five types. Just plucking this out of there. There's no rhyme or reason for this, it might be 10 groups or whatever. I decide on sort of the granularity, and if the data support that sort of classification model, then that's all well and good. So what I've done there, I've done pretty much the same thing that I did with my regression problem, but this time I've got distinct classes, and what I'm going to do is I'm going to use that in a predictive sense. Again, I'm going to basically measure these attributes and apply my model to these attributes, and then use that to classify. So again, this is what's known as supervised learning, whereby I have information, I have complete information on my training data set, so the data I'm going to use to build my model, and then I'm going to use it, we say, out of sample. So we use it on individuals for which we don't know where their correct classification, as it were.
Another big topic in this area at the minute is bias. And as statisticians, we know that bias is just something that we kind of deal with in our modeling, and it's not a bad thing. It's not necessarily a good thing. It's just modeling the real world. So what is your kind of take on the way that bias is now being used as a concept?
Well, I think, one of the dictionary definitions, and I think you will have a mathematical definition there, but the dictionary definition definitely has sort of a pejorative context that, bias is bad. As statisticians, Marie, as you've correctly sort of suggested, bias is merely a statistical quantity. So what we're doing is we're trying to estimate some sort of population parameter. We don't know what that parameter is. We've got techniques for deciding whether our estimate is perhaps too warm, so is an overestimate, or too cold, an underestimate. And simply bias is the difference between what we believe to be the true parameter and what we've actually estimated. And there's no sort of pejorative connotation there. So what's going on? Well, actually, I might actually desire bias in my model. And and I mean, that's a pretty heretical context in terms of what we read about in the media. But for example, if I'm involved in say looking at a rare medical condition in the population, what you tend to find is that any model built with that sort of rarity, you're going to have a lot of subjects that basically don't have the condition. To a large extent, you're not that interested in those subjects that don't have the condition. You want to pinpoint, or you want to basically be able to describe those people that do have the condition. And so I might deliberately bias my model in favor of identifying those people with the condition. It means that I'm probably going to get a lot of false positive results. So I'm going to basically identify people who don't have the condition as potentially having the condition. But what I'm doing is I'm building a model that's actually very sensitive, or more sensitive, to that condition. There are a number of statistical tricks we can use to do that, but that's a perfectly valid thing to do. But my model is biased in that regard. It's deliberately biased. So that is quite different to say a facial recognition system that can't distinguish between a black person or an Oriental person, because the system hasn't been built with those examples in mind. And there's been obviously a lot of media interest in that type of bias, because that seems sort of well, it seems it's pretty bad if that's meant to be a general system, a system for general reuse. And that comes down to basically not having a representative sort of sample in order to train your system, or basically not collecting the right features or variables so that system actually works properly.
It seems to me that it's maybe a language issue. So where we're talking about kind of bias sources in history, we're talking about people that have got a particular opinion towards something. But where we're talking about bias in statistics, we're actually talking about you need to get a representative sample. And if you're missing things out, that's bias by omission. So you're actually, when you're collecting that sample, you're doing what somebody in history might have done and be supporting one particular opinion without all the evidence, which then makes bias a particularly difficult term in language to understand if you're using it in so many different contexts. Do you think there's any way of kind of solving that issue?
I think, I mean, for us statisticians, actually, it's all about being honest with ourselves and honest about our models. So, one of my favorite quotes is from George Box. All models are wrong, but some models are useful. I mean, and that's true no matter how simple or how complex the model is. And I think, the description of the model is always nuanced. There are always caveats there. And it's up to us as sort of scientists and statisticians, mathematicians, to actually be honest about the deficiencies in the model, rather than trying to, I mean, there's no such thing as a perfect model, to sort of portray models as being, all singing, all dancing, perfect representations of what they're about. You mentioned bias by omission. Now, deliberate omission, that's very much a bad thing. And in fact, if you're talking about somebody writing a history book, and that's exactly what they're doing. They may be called into question because they've deliberately omitted evidence that or facts that they should have included in order to give a balanced view of what they're describing. So it does work in a prose sense as well as in a sort of a hard mathematical sense. I think inadvertent bias, and I think I can allow people who build a facial recognition system, for example. So I wouldn't be too aggrieved if I visited China and the facial recognition system that my face was passed through had a problem with it, and that I had to speak to an official, because it's largely been built using Chinese people as the training data set. That seems quite reasonable, and I mean, think if it's clear that that's really what the model was designed to do, then I think that's sort of a fair description.
So another area that we've been talking about to do with this is accuracy and precision. So how important is this in your work?
Well, this is hugely important, actually, accuracy and precision, and the two terms are often sort of confused and used interchangeably, but for us statisticians, again, they mean quite different things. So when we talk about accuracy, what we're saying is, how close to the truth are we? How close to that sort of population parameter are we? And so what we really desire in our models, we want models that are accurate, that basically do get us very close to the quote unquote true answer. Now, precision is really a statement about the model itself. So it's really the how tight am I around the quantity that the model is trying to estimate. The sort of difficult concept to comprehend is that I can be very precise about exactly the wrong answer. So I can be highly inaccurate, but I can be very precise with my model. And we've got a whole range, without going into sort of technical details, we've got a whole range of sort of tools in our armory for sort of estimating these two types of things. And I think probably the best way to describe it is actually a dartboard. I'm aiming for the bullseye. That's where I want to be accurate. But in fact, what I'm doing is I'm more often than not, I'm sort of in the sort of number one sort of quadrant. So I'm off to the top right hand corner, and actually I'm very tightly clustered around that one. So my model, what it's doing actually is it is being very precise about the wrong answer. It is actually highly inaccurate. Obviously, we want both. What we want is a tightly clustered grouping around that bullseye, and then we can say that our model is both accurate and also precise.
Does this cause a lot of problems in kind of modelling where these concepts are just not that well understood? I mean, I
Yeah.
imagine that in genetic algorithms and that kind of thing, where you can be really precise and you can end up in a local minima, and actually that's not where you want to end up at all.
Yes, they can, and people, as I say, people confusing the concepts. They often think that precision is sort of accuracy, and you know, you literally you know, explain the problem very succinctly by saying local minimum. Now that is you know, obviously that's a technical description. We're looking for a global minimum typically, but local minima can exist all over the place, and we might be very unlucky and fall into some sort of global minimum that is a long way from the global minimum that we're searching for. So that's the sort of accuracy that we're aiming for, but we might be in this little pocket somewhere and find a solution that isn't very usable. Saying that, we might be luckier and find a local minima which is closer to the global minimum, and that might be usable. So it's sort of awareness of these things when applying models that I think as scientists we need to sort of express in simple language. I'm not sure that I've necessarily achieved that, because we have bordered on being quite technical today, but I think it's incumbent on us to basically have that explanation there and to explain to our audience you know, what exactly what we're doing, and that you shouldn't just rely naively on numbers that are being spat out by anyone's model. There are some common sense checks that one can apply, and it goes back to what are you actually trying to do. So a clear primary statement of the problem, a primary question, and does the output that you're obtaining, does that, you know, what does that tell you about your primary question of interest? If you can't make that connection, then you know, the model is next to useless. You know, you haven't set it up correctly.
And just to kind of explain just a little bit more, the local minima that we're talking about in the last example, that would be the number on the dartboard, and the global minima would be the bullseye. Is that how we'd phrase it?
Yeah, I think yes. Yeah, I mean that's you know, that's a good analogy from that point of view. I mean, we're bordering on sort of optimization, so that's typically the sort of these are the techniques. So it's numerical techniques that are used to solve difficult problems, and typically the expression of learning, the practical implementation of learning, is in the form of an optimization routine. And one can fit sort of fairly fancy regression models using optimization. In fact, you have to use optimization in order to fit the type of models that I've got in mind. These are things like generalized linear models, generalized additive models that sort of extend our sort of basic regression model.
So final question, what would your top tips be if you were kind of trying to interrogate a model and figure out if it was producing something reasonable, or it looked like it was producing something reasonable, but actually maybe the model wasn't set up right and it just appeared to be doing the right thing? What would your top tips be for interrogating that model?
Well, I think you literally have to link it back to the problem in hand. You know, what does it say about your primary question? And actually, this is often a failing for many studies that I see, that the question that is being asked isn't clear, first of all, or the data that were collected in order to help answer the question were wrong. So there's no way to basically answer the question because of the data that were collected. Very often what I find is that researchers, they don't consult statisticians before they undertake studies, and what they end up doing is they then ask a different question because it's too expensive to go and sort of obtain more data. But you can look at how well the model fits, for example. So we've got lots of techniques for assessing model fit? You know, what do the errors look like in terms of the model? Can I use it actually use it in a predictive sense? It might be, you know, it might seem all well and good in sample, so based on my training examples, but when I've applied it out of sample, I find that it's very poor. Its accuracy is sort of extremely poor, or it just doesn't fit with sort of reality. So from a common sense point of view, and then this is really where the sort of subject matter expert comes in, as opposed to the statistician. I mean, you know, we need to work together with the person who is involved in the relevant field to sort of say, well, you know, I've been modeling an exchange rate here, and I've got some sort of forecast, and they look at that and they say, well, yes, actually, but that currency, for example, doesn't behave like that. So, you know, there you've got a complete mismatch in terms of what the model is saying and what reality is. And it's incumbent on, you know, modelers in general to make sure that that at the end of the day, that it is that what's being produced is actually genuinely usable and sort of fits with sort of you know, common sense and experience.
Well, thank you so much for being a guest today, Richard. We're going to put all your contact details underneath the video or underneath the audio podcast, whichever platform you're watching on. Is there anything you'd like to say just to wrap up?
Well, I would say if you have a data-based problem and you sort of lack experience with models. Models aren't a panacea in themselves. Employ an expert. I'm not saying employ me, but I'm saying, you know, seek advice. And I mean, you know, for example, lots of universities have departments that can provide you with advice in terms of basic data modeling, etc. So seek advice from experts is my sort of final piece of advice.
Some brilliant advice there. Thank you so much, Richard, for being a guest on today's podcast.
Thank you, Marie, for having me. I've been delighted to be here today. Thank you.